So in the last video, we talked about distance, displacement, speed, and velocity. In this video, we will talk about accelerations. Okay. So what is acceleration? Acceleration is a rate at which velocity is changing. Um, we use the word accelerations to refer to an object either speeding up or slowing down. When something is slowing down, we call that decelerations. Okay, and the algebraic equation for that is the change in velocity divided by the time interval. That's the equation for acceleration. Now, is acceleration a vector? And the answer is yes. It is a vector quantity because it is directional. Okay, if you look back at the algebra of acceleration, is the change in velocity over time, and velocity is a vector, so therefore acceleration is a vector. Okay, so if you look at the example in the bottom right here, you have so the question is which car below speed slow down. Okay, so you look at the case one right here, you see that the car is moving to the right with a certain velocity, and also the acceleration is to the right. In this case right here, the car will speed up. Okay, and over here you have a car moving to the right with a certain velocity, but the acceleration is to the left. In this situation, the car is slowing down. A robot is moving in a straight line, steadily increasing its speed each second, first from 10 to 15 km per hour, then from 15 to 20 km per hour, then from 20 to 25 km per hour. What is its acceleration? Okay, I want you to pause the video now and see if you can figure that out and click play when you're ready. To find the answer to this, you have to look at the definition of acceleration. Acceleration is a change of velocity over time. If you notice that the velocity is keep changing 5 kilometers per hour, become from 10 to 15, from 15 to 20, 20 to 25. So the change in velocity is 5, right? 5 kilometers per hour, and the acceleration is 5 kilometers per hour, because again you have divided by the time interval here. So 5 kilometers per hour squared. That's the answer. So right now we're going to talk about motion of a free-falling object. First thing first, what is free-falling? Free-falling is a term that we use to refer to something that's falling on Earth without any air resistance. Okay, because this is introduction to physics, we're going to make things less complicated by ignoring air resistance. So and when we ignore air resistance, the accelerations due to gravity is approximately 10 meter per second square. Okay, to be more exact, it's 9.8 meter per second square. But again, to make things simple, we just say 10 meter per second square is the acceleration of gravity. Okay. It takes 5 seconds for Mr. Dead to reach the ground. How fast will he be going? On the right, you will see the table, and this is number. You can see here, because the acceleration is 10 meter per second square, so therefore every second the speed increased by 10. So the first second is going to be 10, 20, 30, 40, and 50. If you throw a ball upward at an initial velocity of 30 meters per second, then how long will it take for the ball to fall back down, and at what velocity? Pause the video, figure that out, and click play again when you're ready. If you think about it, when you throw a ball upward, right, at 30 meters per second, so during the first seconds, the ball will travel 20 meters per second. The next seconds, you minus 10, so that would be 10 meters per second, and at the top, the velocity will be 0 meters per second. When it go back down, okay, when it go back down, it will have, during the fourth second, is also 10 meters per second, same as the 2 second over here. When it reach this point, which also same over here, have the same velocity, which is 20 meters per second. So during the 6th second is 30 meters per second. So when you throw it up, the initial velocity 30 meters per second. When it's about to hit your hand again, that is also 30 meters per second. Okay, but the whole overall the total trip is 6 seconds. So here's another question for you. If you throw a ball straight down at the initial velocity of 10 meters per second, then what is the velocity of the ball 1 second later? Well, you think a little bit here. You throw straight down, drawing it here. Starting out at 0 is 10 meters per second. 1 second later, what is the velocity? Pause the video. Give you more time. Alright, so what is the answer? Oh, I didn't put the answer here. So the answer would be what? 10 plus 10 would be 20 meters per second. So if you start out throwing the ball 10 meters per second, right? And then it falls down, and then acceleration gravity pull it out even more. So another second, so that would be 20 meters per second during the second seconds. Okay? The answer is 20 meters per second. Let's move on to the next one. If you throw a ball upward at the peak of the path, what is the acceleration? So I'm talking about right here at the top, right here. What is this acceleration? You can pause the video again. Alright, so is your answer? Most people will say that at the peak of the path, the acceleration will be 0. But that's a common misconception because they're thinking about velocity. At the peak of the path means the speed is 0, right? So that doesn't mean the acceleration is 0. Is that everything near the Earth's surface is fall at a constant acceleration. Constant means same, it doesn't change. And that constant acceleration is 10 meters per second square approximately. And so at the peak of this path, the answer should be minus 10 meters per second. Okay, if you consider direction downward. So minus 10 meters per second here, minus 10 meters per second here, right here, right here, right here, and right here. It's all minus 10 meters per second square. That's the acceleration. All right, just don't get velocity and acceleration mixed up. If you drop an object from rest, what is the distance that it will cover in 1 second? I want you to pause the video and see if you can figure that out. Most of you will say that, okay, so if you drop a ball from rest, then it will cover 10 meters, right? Because acceleration of gravity is 10 meters per second squared. So therefore, the first second of fall, it will travel 10 meters. Well, that's the most common misconception. That's wrong. It's actually not covering 10 meters. It's only cover 5 meters only. Okay, so the correct answer is 5 meters. And to figure that out, you need to remember this equation right here. Distance is equal 1/2 gt squared. Some of you might be wondering, how did I come up with d equal 1/2 gt squared? Alright, so how did I come up with distance equal to 1/2 gt squared? And why is it that the ball when dropped from rest travel 5 meters? Okay, so first thing first, if you look to the equation that I'm using is for the system in which I'm dropping a ball from rest. I'm not throwing it down, I'm not throwing it up, I'm just dropping it from rest. Where I'm going to define the position in which I start dropping it is, I call that the starting distance, initial distance di is 0 meters, and the starting velocity vi, velocity initial is 0 meter per second, and the ti is starting time is 0. Okay, so what I'm looking for is df. So in order to come up with the equations, this equation that you will be using for free falling object at rest, you start out with the definition that you have learned before. You learned before that the average velocity is nothing more than df minus, df stand for distant final, minus distant starting, the initial over t. And in this particular case, you know that you can cross out di because di is 0. So let's just cross that out. Okay, so what you have left is you have df over t. That will give you your
average velocity. And so if you just multiply both sides by t, right, then that'll give you t v equal to df. Okay, so notice how I'm going to say this equation number one. Equation number one is not the same as the one I use on top up here, right? Up there it is 1/2 gt squared is not t time average velocity. Okay, so I need to make equation number one look like the equation on top that I will be using a lot. So how can I do that? So we can start out say, you know what, there's something that I need to change in this equation, maybe the average velocity. So what is the definition of average velocity? Starting velocity plus VF divided by 2, that will find the average. And that's how you find you add two numbers together, divide by 2, right? And again, the initial velocity here is 0 because you're dropping object from rest, so you can cross that out. So what you have left is you have VF over 2, that's equal to your average velocity. Okay, this right there. So I'm going to call that equation 2. If I take equation 2 and put it into equation 1, let's see what happened here. Let's add the 2 together here. Put it, I shouldn't say add, just put it into equation 1. So if you put average velocity, so you have t, and the average velocity is vf over 2, that's equal to df, right? So I have another one that I just came up with, and that doesn't look anything like the one on top still. So what should I do? I know on top have g, and g is reversing acceleration. So maybe I should use the definition of acceleration to make it look like the equation on top. So let's say, what is acceleration? Acceleration is defined as vf, right, minus vi over t. And again, in this particular case where the starting velocity where you're dropping an object is 0, so what you can do is you can cross this out and you can have equal to Vf over t, that give you equal A. So when you manipulate this equation, multiply by t on both sides, you have t times A equal to V of F. Okay, and what is A? What is A? A, because the object is dropping near surface of the Earth, A is actually equal to 2. I mean G, I'm sorry about that. A is equal to G, and which is equal to 9.8 meter per second, but I'm going to use approximately 10 meter per second square, okay? So I can replace this equation over here. Instead of A, I just say TG equal to VF. Okay, now it start to look close to what we have on top. I'm going to take this. I'm going to take that VF. I'm going to put it in here and see what happened. Okay, so I'm going to copy the same equation down. T over 2. VF is nothing more than TG, all right, equal to DF. So there you go. So if you clean up this equation up, it just becomes G. T times T is T squared. It's just over 2, so that's the same thing, 1/2. That's df, and that's the equation that we will be using a lot when we have an object dropping from rest.
If I drop a small object and a large object at the same height, no air resistance, which one will have more speed and which one will have more acceleration? So let's see if we can solve the first one first. If I drop a small object and a large object at the same height, no air resistance, which one will have more speed? Pause the video. The answer is they're both going to have the same speed because they both have the same accelerations. Okay, and this is neglecting air resistance. So because we have, if you take a textbook and a sheet of paper and you drop it, of course the textbook gonna hit the ground first. Okay, and of course the textbook going to move faster than a sheet of paper. The reason for that is because of air resistance. Okay, but if you crumble up that sheet of papers and you drop it next to a textbook, do the experiment yourself. You will realize that both will hit the ground at the same time. The other cool experiment that you can do is if you take like a textbook, not your iPad. You don't want to drop your iPad, but just take a textbook and put a sheet of paper in the bottom, okay, and drop it. Or you put a sheet of paper on top right here where you kind of remove that air resistant component and you drop it. I want you to check and see what happened to that sheet of paper on top. Does it travel the same speed as the textbook or it's just floating in the air? Try that yourself.